hope nothing fails here. Okay, good. All right, so screen share. Great.
Do I need to keep it?
Yeah, you can have one. Okay, for Zoom participants, can you hear me out there?
Yes.
Yes? Okay, good. All right, let's begin class. So again, let me remind people that the midterm is going to be in week 11. So let me give you the dates again. So there are 2 sessions for the midterm. So this is the second midterm. The Bulldogs go first this time. And supposed to come in Wednesday, the 4th of November. And the people who are Georgia's will come in Friday, 11/6. Okay, and then, so next week is a short week. So I will lecture on this material until Monday. On Wednesday, we'll have part 1 of the review, and then the following Monday, we'll have part 2 of the review. Okay. Okay, any questions? All right, so we are talking about eigenvectors and eigenvalues. So let's go to this. So eigenvectors and eigenvalues. All right. Okay, so let me kind of remind you what an eigenvalue is and an eigenvector. So A is an m by n matrix. And so if I take x, which is not 0, such that AX is equal to lambda x for some lambda, then X is an eigenvector for the matrix A. Okay. And lambda is an eigenvalue for A. Okay, so that's a definition of an eigenvector and an eigenvalue. Oops. Sorry, let me get back in there. All right, so what we did last time was we kind of outlined a plan for how to determine eigenvalues and eigenvectors for A. So let me kind of recall this idea. So suppose X is an eigenvector for the matrix A. So then we have AX, oops, let me erase this for a second. We went a little bit too fast here. So then we have AX is equal to lambda times X. And this happens if and only if AX minus lambda X equals 0. And this happens if and only if A times lambda on the identity on X is equal to 0. And since X is not equal to 0, that means that A minus lambda I has a non-trivial solution. So that means that the determinant of A minus lambda I must be 0. Okay? So to find eigenvalues, we just want to know when the determinant is going to be 0. So set PA of lambda to be equal to the determinant of A minus lambda I. Okay? So PA of lambda is called the characteristic polynomial for the matrix A. All right, so you have a matrix A and then you form its characteristic polynomial by taking A minus lambda I and taking its determinant. We'll do some examples in a second. Okay, so the main point is the roots of PA of lambda are the eigenvalues of A. Okay, so we have this polynomial that we actually form. We look at the roots. Those are precisely the eigenvalues, right? Now, once you're given an eigenvalue, you can find all the eigenvectors by just looking at the eigenspace. So let me make that clear. So let lambda be an eigenvalue of A. Okay? So the eigenspace of lambda equals the null space of A minus lambda I. Okay, so this is a subspace of Rn, right? Because we know that when you take the homogeneous solutions, then we actually get a subspace. So this is a subspace of Rn. And we know how to compute null spaces by just using Gaussian elimination. on A minus lambda I. So we can just use Gaussian elimination, and we actually know how to find a basis for this too. Okay, because we just look at the free variables and then we look at the vectors next to the free variables in the solution, and that gives us a basis. So let me just say parenthetically, one can compute a basis using Gaussian elimination. Okay? And then the non-zero vectors in null are just the eigenvectors for lambda. So the eigenvectors of lambda are the non-zero vectors in the null space of A minus lambda I. Okay. So what I've done here is I've outlined how to actually find the eigenvalues first. And then once you have an eigenvalue, you can actually find all the eigenvectors corresponding to that eigenvalue. Okay, any questions on this? Questions? No? Okay. All right, so what I'd like to do now is I'd like to do an example. We'll just do a nice 2x2 example. We'll find the eigenvalues, and then we'll actually find the null spaces corresponding to each eigenvalue, and that'll give us the eigenvectors. Okay? So let's do an example. All right, so A will be equal to 3 minus 4, 4, and 8. Okay. All right, so now I need to form PA of X. That's going to be the determinant of A minus lambda I. Okay, so what do? I take the matrix A here, and I subtract off lambda from the diagonal. So I get 3 minus lambda minus 4, 4, 8 minus lambda. Okay, and we just continue on. So I just take the determinant of the 2x2 matrix, AD minus BC. So 3 minus lambda, 8 minus lambda, minus a minus 16. Okay? So now you have to just, write everything out. So this is going to be 24. What's the middle term? Minus 8 lambda, minus 3 lambdas, minus 11 lambda, plus lambda squared, and this is plus 16. Okay? So this is going to be equal to lambda squared minus 11 lambda, and then plus 40. All right, so this is the characteristic polynomial for A. And notice what the degree is. So what's the degree of this polynomial? 2, right? So it's a degree n polynomial. So this has degree 2, which is equal to the degree of, which is equal to n, sorry. I goofed up again. Okay, let's erase that. Let's go back. And that's equal to n. Okay, the degree is equal to 2. It's equal to n. Okay, so what's the next thing we have to do to find the eigenvalues?
Find the roots.
Okay, can you speak up a little bit?
Find the roots.
Yeah, hang on, let me jack the volume up here. Okay, one more time.
Hello, hello.
Yeah, okay, just find the roots. Can you say that
Yes.
again?
Find
Okay.
the roots.
Find the roots. Thank you. All right. So how do we find the roots?
Set that equal to 0.
Okay, we set it equal to 0, but how do you find the roots of a quadratic polynomial?
Quadratic formula.
Yeah, so we can either factor or use quadratic formula, okay? All right, so let's use a quadratic formula here. So lambda is equal to, okay, so minus b, that's 11, plus or minus b squared, that's 11 squared, minus 4, a is 1, c is 40, all over 2 times a, which is 2. Okay, everybody all right with that so far? Okay, this is the quadratic formula. Let me just write it in. Quadratic formula. All right? Okay, so now we just have to simplify things, okay? So this is going to be equal to 11 plus or minus the square root of, let's see, minus 39. Okay, so you do all the arithmetic in there. It's minus 39 over 2. Okay, so this is going to be 11 plus or minus I times the square root of 39 over 2. Okay, and here I is equal to the square root of minus 1. So are the roots real or, totally complex numbers?
Complex.
Or complex. Okay, so these are complex eigenvalues. So you can get complex eigenvalues. All right. So there are 2 of them. And I think that's all we want to do. Okay, so the problem here is just, so the problem I should state more clearly is find the characteristic polynomial and the eigenvalues. All right, so that's what we want to do with this problem. All right, so we won't find the eigenvectors. We'll actually do another problem where we do find the eigenvectors. Let's see. I guess we did do a problem using the eigenvectors, but let's do another one. So here's another example. Find the eigenvalues of the following matrix, and that's A equals 4, 0, 0, okay, 5, 3, 2, and minus 2, 0, 2. Okay, so not quite lower triangular. So, all right, so we have this matrix, and basically we just do the same thing, except it's a 3 by 3 matrix instead of a 2 by 2 matrix. So what's the degree of the characteristic polynomial going to be? 3. Okay, so let's make sure it's 3. Okay, so if I take PA of x, or PA of lambda, what do? I subtract off lambda from the diagonal and put the rest of the entries in. So I get 4 minus lambda, 0, 0, 5, 3 minus lambda, 2, minus 2, 0, 2 minus lambda. Okay, is everyone okay with this so far? So this is the determinant of A minus lambda I. Okay? All right. So now what we can do is we can just use cofactors, right? And if we expand along the first row, the only time we ever get a non-zero entry is using the 4 minus lambda, right? So we just take that coefficient 4 minus lambda, and then we take the cofactor, right? So what do we get? We get 4 minus lambda. And then the cofactor, I'll just write it out. It's C11. Okay. And then the rest is 0 times C12 and 0 times C13. Maybe I should write this out. Okay. So you notice that the only time I have to worry about is I have to worry about the factor involving the 4 minus lambda. All right, so let's do this. Let's continue on. This is 4 minus lambda. C11, we have -1, the 1 plus 1. Okay, and then we take the matrix, we just take the matrix we get by crossing out the first row and the first column. So I get 3 minus lambda, 2, 0, 2 minus lambda. Okay, so then I get 4 minus lambda, and then I get a product of 3 minus lambda, and I get a product with 2 minus lambda. Okay, so of course we want to look at the roots. So we set that equal to 0. So what are the eigenvalues in this case?
4, 3, 2.
4, 3, 2. Okay, so lambda, I'll just write it the other way, 2, 3, 4 are the eigenvalues. Okay. Any questions on this? How we did this? All right, good. Now, before we go on, I'd like to talk about something called similarity. And then we'll do more examples using eigenvalues and eigenvectors. So I'll actually bring the eigenspace in a moment, okay? So let's talk about this notion of similarity. All right, so here's a definition. So let A and B be n by n matrices, okay? So we say that A and B are similar, okay? If there exists an invertible matrix P which is also n by n, such that I can get from one to the other by just doing some type of conjugation. So A is equal to P, B, P inverse. Okay, so the idea is that we want to look at matrices where we can get from one to the other by applying an invertible matrix to one on one side and the inverse on the other, and we can actually produce the other matrix. Okay. Now, there are very nice things that happen with similar matrices. So the first thing we're going to observe is that the eigenvalues are always the same. Okay. All right, so maybe I'll make a remark. So maybe if I make a remark, so if A is similar to B, then it turns out that B is similar to A. Okay. Just replace P by P inverse. All right, so now let PA of lambda be the characteristic polynomial for A, and PB of lambda to be the characteristic polynomial for the matrix P. Okay, so now let's analyze the characteristic polynomials if A and B are similar. So here's the theorem. So if A and B are similar, then PA of lambda is equal to PB of lambda. Okay, so therefore, A and B have the same eigenvalues. So, if they have the same characteristic polynomial, the roots are the same for both. So they have the same eigenvalues. Okay. All right. So this is not so bad. So here's a little bit of a proof. So suppose, they're similar. So A is going to be equal to PB P inverse. Okay. So now what we should do is we should just take minus lambda times identity on both sides. So if I take A minus identity, lambda times the identity, this is PB P inverse minus lambda times identity. Okay, so I'm just subtracting off minus lambda identity on both sides of that equation. And now you can write the identity as P times P inverse. So this is going to be equal to PB P inverse minus lambda times P inverse. Okay. And now what we can do is we can distribute the P out on the left and the P inverse out on the right. So this is P B minus lambda times identity times P inverse. Okay, is everyone with me so far? Yeah. All right, now, ideally, what you'd like to do is you'd like to sort of knock the P and the P inverse out by just switching B minus lambda I and P inverse. But that is not allowed because the matrices may not commute, right? However, we're not looking at this equation to get the characteristic polynomial. So what should we do next? Anyone? How is the characteristic polynomial defined?
Take the determinant of both sides.
Right, so we should take the determinant of both sides. So that means that the determinant of A minus lambda I is equal to the determinant of P B minus lambda I P inverse. Okay, so now what can we do? If I take a product of matrices and I take its determinant, what's it equal to?
Out of the determinants.
The
If I take
product
a
of
product, sorry, go ahead, someone said it.
the product of the determinants of each individual term.
Yes, very good. So that's the determinant of P times the determinant of B minus lambda I times the determinant of P inverse. Okay. And now you're allowed to switch P inverse, determinant of P inverse with determinant of B minus lambda I, because they're just numbers. Okay. So now I'm allowed to do this. So determinant of P, determinant of P inverse, determinant of B minus lambda I. And then if I want to do this, this is the determinant of P times P inverse times the determinant of B minus lambda I. But P times P inverse is identity. So that's the determinant of the identity times the determinant of B minus lambda I. So that's determinant of identity is 1. So this is the determinant of B minus lambda I. Okay, so I think I gave all the steps that one needs to do. All right, so on one hand, okay, let's switch colors a little bit. I guess we're not playing football this weekend, but we'll go with the red. Okay, so this is PA of lambda, and at the end, this is PB of lambda. Okay, so we'll put the little tombstone down to signal the end of the proof. Okay, any questions on this? Okay, good. All right, now why is similarity useful? Well, it's useful because it makes computations easier in many cases. So let me give you an example of how similarity can be used to sort of figure out computations. All right, so this next thing is called diagonalization. Oops, go back to this, erase, and let's go back to the black. Okay, so let's talk about the notion of diagonalization. Okay, so the idea is the following. We want to know when A is similar to a diagonal matrix. Okay. Now, suppose that this is true. Okay. So suppose we do have this case. Suppose A is similar to D, where D is a diagonal matrix. Okay, so suppose you have A being similar to D. I think you might have done this in your homework. And so suppose I want to compute like a matrix to the 1000th power. Okay. So it turns out that if you know that A is similar to D, and if you know what the P and the P inverse are, then you can do this rather easily. So if I take A, which is going to be PD, P inverse, what happens when I take A squared? This is PD, P inverse, PD, P inverse. Okay, so what happens with the P inverse and the P? What do we get?
They make an identity.
Right. So this is going to be equal to, let me just write it out formally and then you'll get the idea. So here's a D, P inverse P, D, okay, P inverse. So this is going to be P, D squared, P inverse. Aha. So we see a pattern going on here. All right, now you just repeat the argument. So what's A cubed going to be?
P D cubed P inverse.
Good. Okay, so then A to the 1000 is equal to P D d to the 1000 p inverse. Okay? Now, let me ask you a question. So you take a matrix, say, and it could have lots of non-zero entries. Let's say it's a big matrix, even like a 5 by 5 matrix. Now, do you want to take that matrix and multiply it to itself 1,000 times? Now, you probably spend all day doing it, right? But how about if you have a diagonal matrix? Like just things along the diagonal. Is it easy to multiply that matrix out 1,000 times?
It's
Well, I
easier,
mean-
yes.
So let me ask you this question. So just from a very practical viewpoint. So suppose the diagonal matrix is A11, A22, and N, with zeros everywhere else, okay? So what's D squared gonna look like?
It would be each entry along the diagonal squared.
Good. All right, so what's D to the 1000? Anyone?
Each entry along the diagonal to the 1000th power.
Good. All right, so I ask you again, what's easier to compute? A to the 1000th in general or D to the 1000? Right. So now you can almost see how it's much easier. Once you have a decomposition of A as P, D, P inverse. All right, so let me do a problem. Let's do a problem that involves some numbers. All right, so here's my A, and the A will be -2, 12, -1, 5. Okay, it's a 2 by 2 matrix. And so it turns out to factor as the following. So here's 3, 4, 1, 1. And then the diagonal part, I'm just giving this to you, but we can actually figure it out. And then the third part is -1, 4, 1, -3. Okay, so this is your D, and this turns out to be P, and this turns out to be P inverse. Okay? You can just check that out.
Wait, shouldn't it be 1, -4, -1, 3 on P inverse?
One,
Or did I forget something?
let me see. I think you have to divide by the determinant. Yeah, you have to switch the entries, but you have to divide by the determinant. Okay. All right. Okay, so I have this decomposition. Really nice. Okay, so let's take A to the 1000. So if I want to compute A to the 1000th power, well, I don't want to do -2, 12, -1, 5, and multiply that out 1000 times, right? So this is going to be P. And as we've seen before, you just raise all the powers to the 1000. So 1 to the 1000th is just 1, okay? And then P inverse. All right? And if we want to write everything out, we can. 3, 4, 1, 1, 2 to the 1000th, 1, and then I'll just write the other matrix in. Okay. All right, so we'll matrix multiply the first one. So what do we get? We get 3 times 2 to the 1000, okay? And then the next one's a 4 here. And then I get 2 to the 1000, and I get 1, okay, times this matrix. Okay, I just matrix multiplied the first 2 matrices over there. Everyone okay with that? All right, now I just matrix multiplied these 2 matrices. So let me just make sure I have no space. So I get minus 3 times 2 to the 1,000. So I'm taking the dot product of the first row with the first column, right? Plus 4. And the next one I get 12 times 2 to the 1,000 minus 12. Okay. And the third one I get minus 2 to the 1,000 plus 1. And finally I get 4 to the 1,000 times 2 to the 1,000 minus 3. Okay, any questions on this?
So is this, so this is only more efficient when a to the n where n is greater than 3, because you have to take the dot product essentially.
Well, I think multiplying 3 matrices is not so bad compared to multiplying a matrix times itself, let's say 1,000 times.
Right, okay, that makes sense.
The whole point is that the diagonal matrix is like super easy to compute to the 1,000th power. You just raise each entry to 1,000th power. And then you just have to matrix multiply the other side, right? You know, three matrices multiplied together. So it's pretty impressive. I mean, you pretend I just give you this matrix. I can't cover things up, but just pretend I give you minus 212, minus 15, and I say, I want to know what a to the 1,000th is. And so, you know, you could try just, you know, multiplying it out. But if you have a decomposition like this, you know, eventually you can actually write it in this very nice form via the eigenvalues of A. So the entries, remember, the eigenvalues of A are the same as the eigenvalues of the diagonal matrix. Okay. Because they're similar. Okay, any questions? So this is why eigenvalues are quite important. Yeah, go ahead.
Who do you think how to get the
Yeah, I was going to ask that question. All right, so what's the next question? What should be the next question? Oh, I
How do
think
we
you
get
could
paid?
ask it.
yeah, how do we
All right, so so this is related, of course, or this is the same idea, is when is A similar to diagonal matrix? Okay. Right, so I have to tell you, I have to say like what the answer is, right? I mean, I have to sort of say, okay, you have an m by n matrix, I want to know when it's similar to a diagonal matrix. So what I'll do is I'll say when it's similar to a diagonal matrix, and then I'll say how to get the decomposition. Okay, and that will answer both questions. Right. Okay. All right, so here's the big question. When is A similar to a diagonal matrix? And it turns out that, you know, some matrices are similar to diagonal matrices and some matrices are not. Okay, so we want to know exactly when that's true. All right. All right, so set V lambda equals the null space of A minus lambda. Okay, so that's just a notation. Okay, so this is called the eigenspace. Okay, so here's the theorem. Okay, so A, let me just state it first. Let me be a little bit more careful. Okay. So let A be an m by n matrix. All right. So statement number one, A is similar to a diagonal matrix okay, if and only if when I sum the dimensions of the eigenspaces, then I get in. So what I do is I just take all the eigenvectors for A, and then I compute the dimensions of the null spaces for every single one, and I just sum up those dimensions. And if the answer is equal to n, then it's similar to diagonal. Okay. All right, now two. It turns out that this is also the same. So P is equal to PD the inverse. So A is similar to diagonal matrix if and only if P consists of eigen vectors of A. All right, so to actually get the P, I have to go to compute the eigenvectors of it. So once I have enough of them, this is the first statement guarantees that I'm going to have n of, n linearly independent ones. And so I can just put them down the columns of P, and then that will give me P. Okay. Let me just say it this way. When I say consists of, i.e. P is equal to, let's say, V1 up to Vn, where the Vj's are eigenvectors. Okay. Okay, so first of all, are there any questions on this?
So in the example earlier, 3, 1 and 4, 1 were eigenvectors of A.
3, 1. Which example?
The example that we did right before this theorem.
So the yes, that's right. Very good. So 3, 1 and 4, 1 are eigenvectors of A. Okay, so that's a good point. So back to the example. The eigenvalues are lambda equals, let me go back, 2, 1, right? And you can actually look at the eigenvectors and like you're saying, there are 3, 1, and 4, 1. Okay. And so 3, 1 is an eigenvector for 2. They line up 2, all right? So it turns out that this is, let me just write it this way. So 3, 1, this is an eigenvector for lambda equals 2, and this is an eigenvector for lambda equals 1.
And we
Okay.
found these eigenvalues from the diagonal matrix 2, 0, 0, 1.
Yeah, so we know that, remember that if you take two similar matrices, then the eigenvalues are the same. And the eigenvalues for diagonal matrices are just the entries along the diagonal.
Right. Okay, that makes sense. So this is just kind of a property of eigenvectors and eigenvalues that's
Oh, yeah.
computationally useful.
Yes. And so this technique in linear algebra is extremely important because it allows us to compute things that normally we would not be able to compute, or it'd be very difficult to compute if we did things by just brute force. Okay. All right, so let's see. I'm running out of time. So what I'm going to do is I am going to stop here because I want to actually give you some justification for this theorem, and then we'll do some examples afterwards. So I'll come back to this main theorem. This is actually a very, very important result that we're going to be using all the time. So I want to spend some time with it at the beginning of the next class. Okay, on Monday. All right, any questions? Okay, if not, please have a safe weekend.
Thank you, Professor.
Welcome. Yeah, go ahead.
So, from what you gave us the whole one with the relation of all the dimensions of d lambda.
Yeah,
Couldn't we just count how many solve eigenvectors if the amount of eigenvectors equal n? If they vary the diagonal.
yes. So I was about to say something like this.